Hello friends, so in this video lecture we are going to check the design and analysis of a tall building due to the earthquake only. Means uh, we will apply the earthquake load only over all the building. Okay, over the building we apply only the earthquake loading, and we will see the results of design and analysis both. So I take it as a structure wizard. Now files, select units that should be in meters, okay, and take the frame model, bay frame, and I take it as 2 along the height. You can take it as 10, we can take, and this is okay 3 by 3 कर लेते हैं. 3 by 3 is more fine. 15 and 10 by the 10 10 10 10 30 30 meter is okay. 12 3 4 4 okay, apply. So this is like our tall building that we have to design. Cross, yes, and then okay. So this is the building. Now you have to assign the properties, select define, and go to the rectangular. I take the 0.35 and 0.35 same for all the beam and for the columns. Okay, this is for all the sections. So assign to you, I have assigned these to all the beams and all the columns. Now go to the material and click on concrete, double click on concrete, select the compressive strength 30,000 kilonewton per meter square. Now supports, we have to create a fixed support. Now assign this at the bottom joints. So shift and right click over all the over the window and select the bottom nodes. Assign, yes, this is perfect. Now go to the loading. So we have to just apply the dead load and what? Dead load and what? Earthquake load. Because I want to design the earthquake resistance building. So if I will build a building, so I'll design and I build the building, and there is not any load should be applied. Okay, so there is not any load will be applied. So there is the loading. Those are applied only dead load and earthquake. Okay, so there are two types of loading: dead load and earthquake. And you can take the wind load also if you want. Then you can design the wind resistance building also. But I in this lecture I will design only earthquake. In the next lecture we will design the wind resistance. So that will not issue. So in this lecture we are taking the two types of dead loads, two types of loads cases. First one is our dead load, in which we put the self hit and just build the building and apply the earthquake. How will the building will respond, that we want to see. Okay, तो हमारा बिल्डिंग कैसे रेस्पॉन्ड करेगा जब उस पर अर्थक्वेक अप्लाई होगा. जस्ट डेवलप मीन्स बिल्ड बनने के बाद बिल्डिंग हमने रेडी कर दिया. बनने के बाद हमें उस पर कोई रहने नहीं गया. अभी कोई भी हमने रेजिडेंशियल बिल्डिंग है तो कोई रहने के लिए अभी हमने फ्लैट कोई भी नहीं दिए. तो उस पर क्या होगा, कोई भी डेड लोड लाइव लोड कोई अप्लाई नहीं होगा. ओनली डेड लोड है मीन्स बीम कॉलम था ही, स्लैब बीम कॉलम, एंड ओनली अर्थक्वेक आ गया उस टाइम. तो तुम्हें देखना है कि वो उसमें सेफ है या नहीं, क्योंकि there is up to the certain limit the live load will help in the resistance to the earthquake, because that will be applied in the downward direction. So if your weight is very high and earthquake will happen, so there is less possibility that you will fall down. Okay, there is less possibility because the friction force will be more. Because the friction force will be more, what the friction force, mu into n, mu into weight. So if your weight will be more, then the friction force will be more. You can't fall down very easily. Okay, so that's why we are studying about only dead loads and earthquake. So first of all I have checked the seismic edge, earthquake in x direction, enter, control a, earthquake in z direction. So you can take anyone. Okay, z we will take, that is so okay. Dead load once again, dl, no dl. Okay, just close it. Earthquake in x direction, add. So earthquake means we have to just first of all define. So now go to the seismic definition, click on add, select the code 2016, generate, and select the city. So I take it city as the Delhi. Okay, I take it the city as Delhi, and this is our RC building with ordinary moment resisting frame resisting beam. Okay, OMRF building है, and this is like residential. The soil is medium, and all other buildings. Damping ratio, for the RCC structure we take it as 5%. Click on generate, add. For the sulfate you can take the sulfate factor, and if you want to add some floor weights, because there is only dead load, so you can take the dead load as fully floor weight. uh, because in the seismic weight I have give the idea about these things, that if the live load will be less than 3 kilonewton per meter square, listen to me, because I am not writing these things on the screen. If the live load is less than 3 kilonewton per meter square, then you have to take the 25% of the live load as the seismic load. Seismic load means floor weight. Okay, and if that will become more than 3 kilonewton per meter square, what live load? If live load will become more than 3 kilonewton per meter square, then you have to take the 50% of that live load as the seismic weight, means floor weight. Okay, so let's example we take the floor load, means live load, as 4 kilonewton per meter square. That means we have to take what, 50% or 25%? We have to take 50% of 4 kilonewton per meter square. That will come out as 2 kilonewton per meter square. That is the contribution of the live load in the floor weight. But for the dead load we have to take 100% of dead load, you know. So I calculate in the calculator. What we have to do, first of all, we have to take all the seismic weight, all the dead load in the seismic weight. So dead load is what? If the concrete density is 25 and the thickness of the slabs, that is 150 mm, so that will come out as 3.75, and we have to plus what, 50% means 0.5 of, yeah, that's a problem. Okay, 3 point, I write it again. Calculator. The floor weight is, the dead load is 3.75. We have to take the 0.5 times of what, 4, so that will become 2. I write it directly. So that is our 5.75 is our what, seismic weight. So you can go through the course also, IS 1893 2016, and you can go through my video also, seismic weight. That in that video I have covered these things also, so there is not an issue. So in the y direction you can take it as 50, because the overall height is 30, so you can take much more higher than this. Add. Okay, then close. Now go to the earthquake. In next direction you can define it easily, earthquake load, x direction plus 1 factor, add, close. And for the z direction you can take it as seismic load in z direction. Okay, add, close. Now dead load you have to take. What is the dead load? Yes, sorry, I have done one mistake, that we don't have to use the what, live load. In the explanation I have done some mistake, that because in this video we don't take the live load. I have covered this thing in the starting of the video, so you have to just take the 3.75. Okay, because we have to take 100% of the dead load and 25% or 50% of the live load as per the condition for live load. Okay, so I modify it. Okay, that's done. Now go to the dead load and assign the what. You can assign the, first of all, sulfate. For what? Sulfate for the beam and columns. If you assign this is assigned to you, then it will assign only for the beam and column, but there is the slab also. So in the dead load you have to assign the floor weight. Floor load is what, negative of what, 3.75, that we have calculated up to the 50 meters you can take. So if you see, these are the loadings. Okay, there is not an issue, I think. Okay, so now you can make the load combinations also here. Auto load combination by the, choose your code, IS table number 8, that is okay, and then add, close it. And now go to the analyze and define command, all, add, close. Okay, and if you want to show the, if you want to see the modes also, so I have already done these things in one of the my one of my lecture. Add the frequency, model calculation, consider missing mode shapes, add. So this thing as I have done earlier in one of my lectures, one or two I think. Just run analyze and then okay. So you can show two warnings, two errors are there. So what are that? I first see warnings are not mandatory. Unsupported masses enter check density. Okay. Um, is that where? Okay, I check it again. I remove it first of all. It may cause some problem, I think. Okay. So in dead load you can put that thing. That will not affect. So in dead load I put the frequency as model. Check it. If it will fine then okay. We can see the modes. Missing, delete, requested and analyze and assign. Okay. Now we can see that is work or not. Okay. That is fine. So now we have to go to the post processing, and the post processing you can see all the mode shapes. So here you can see the modes. There are 6 type of modes. If you want to see the animations then you can see of the modes and then okay. So this is the first mode due to the dead load, only due to the dead load, because in dead load we have assigned this thing. Okay, this thing is assigned only in dead load. Mode number 3, that is our mode number 4, that is our mode number 5, and this is our mode number 6. So okay, this not my interested thing that you can do by your own. So now we have done the analysis part. You have to just go for what? You have to just go for the design. So you can select what? Advanced concrete design also here. So you have to just go for advanced concrete design, and I have given the sequence for the design procedure already to you, that you should design first of all slabs, because the slabs are the main important thing that you should know. So you can, so because you know the loading is same I think. So first of all you should design 3 meter at the 3 meter level slab. Okay, so you can design it. So this is not a big thing because these things we have done in previous lectures also, but I want to give some idea that. So this is your view from the plan, you can see it. So 2-way slab it's okay, yeah, because the ly by lx ratio is less than 2. You know the ly by lx, how to define the slab as 2-way and 1-way slab. So I give you some idea that if the ly by lx ratio is less than 2, then it is the 2-way slab. Okay, and it's greater than 2, then it will become 1-way slab. And there is one more condition is this: if the slab is supported from two opposite sides. Okay, I will give this thing in the slab design, no problem. So we go for settings, design parameters. You can curtail and bent up bars provide. So bent up bars if you provide, then these are the things that you know. You have to just modify by M30 and take the M550. 20 mm is the cover, but this is not okay. 25 you can take. Minimum thickness I have take it as 150. Minimum spacing, maximum spacing, that is on this type. Crack width we don't want. Now auto design. Yeah, I should. So this is 0. This is, we can take it as a what I Okay, 000 not 3.75 it will come. Yeah, control V, 0, and design. So you have to take some value. So I take it as 0.1 because it will create some issues. Yeah, this okay. For the value should be okay 1, minimum 1. So I change it by what, 2.75, and change it by 1 to this. Now it will work. Okay. So these are the detailings of the reinforcement. So these all are green. So green means the design is safe. You can see all the reports. So it's not, I think I should not go through these things. You know all very well that how to create the BBS and detailings also. So this thing is clear, I think. So this is the design of slab. Okay, this is the what, design of slab. So it's clear. Now I go to back again. If you want to save, then you can save it. So you can make the AutoCAD file. I have told you that how to make the AutoCAD file we can generate from the RCDC, means advanced concrete design. So now go on for beam designs. Okay, so beam designs, first of all I accept this beams. You have to click all over the slabs, all levels. That's the issue. So this is okay. Now go to the setting, general reinforcement. So ignore torsion, ductile design. We want to do the ductile joint at the shear and or what. Okay. Flange beams if you want to give, then is okay. Best fit, yeah, that's okay. 0.2%. Perform check, design code, and I just want to change these things. Not the third. That is a second for also be 500. Clear cover is take it as like 30. Maximum aggregate sizes, so I take it as 20. 20 is okay. 8 and dian 75, and then this is okay. Now go for next. Rebar curtailment, this is okay as per the code. You don't have to change these things. Detailed drawing, that is the already according to the code, so that is okay. I think there is nothing to change. Yeah. So effective span for the curtailment, if you want to change it, then you can change center to center or clear span. Preferred bar spacing, that is okay. Basic load cases, we have to select all the things. This is our seismic in X direction, earthquake in X direction again, Z direction, sorry. And this is our dead load. Select this one, transfer here, okay. Add from analyze, that is okay. Now design. So it's running for the design process. So I want to just show you that the design is fail or not. So our design is safe. Okay, there are all the things that you can see. Shear, top right, SFR, there is not any need of SFR. Can anyone tell me that why the SFR is not needed here? SFR, sad face reinforcement, and I have give the idea about SFR in any, I think, last lecture. in the last lecture of RCDC in the beam designs, I have given the idea about the SFR. When we have to give the SFR, 0.1% of the cross section area, the quantity of SFR, I have told you. And if the torsion is applied, then we have to take what, 350 mm. If more than 300 mm, sorry, if more than 300 or I think 350 mm, then we have to provide the side face reinforcement. If the depth of the beam will increase uh, there is one limit, I think that is 350 or 450, I don't know. uh, but if the limit will cross that, then we have to provide the side face reinforcement. But here the depth we have take it as what, 350, that is already a 350 mm, so there is not any possibility that we can provide side face reinforcement. Okay, so now this is okay. So I complete this video up till here because there is nothing to do that I have to give other another design parameters like columns and footing. You can do by your own because that thing is same as previous. Okay. So friends, we have designed and analyzed this type of structure, 10-story building with 3 meter height. The story height is 3 meters. So I have modeled this in SAP also because I want to show you that how the earthquake will happen and it will goes where, means the animations I want to show you the mode shapes. So how it will affect, so I run it and run now. So this is the same model that I have made in the our Staad Pro also. Okay, so this is the first mode that you can see. I start animation, that's gone like this. Okay, this is our first mode. Now I go further. If you want to see the first mode over here, then you can see this is mode 12. Sorry, this is in the left screen, that is mode 12. I change it for mode 1. Yeah, okay, that's now it's okay. So you saw that this is the mode 1. Okay, so if the earthquake has the frequency like 0.6989, if you want to note down how to make the frequency, so I have seen this type of calculation. You have to just multiply by 2 pi with what, 0.69 means 0.6989, that will become as 4.3. So it means if the frequency of the it means that what, if the frequency of the earthquake is equal to 4.38, then the building of our that the at that frequency of earthquake, our building will respond like this. Okay, this is the response of our building during this natural frequencies earthquake. Okay, so now if I will increase the natural frequency, means the ground excitation frequency is become more, that will become up to what, go to the second mode that have the frequency like this. So you can calculate it again by the what, you have to just multiply by 2 pi by the what, 2.139, that will become 13.43, means 13.43 radian per second. If the natural frequency of what, if the frequency of the earthquake become this 13.43, then our building will respond and deflect and mode will like this. Okay, so I run it again, so you can show both of the diagrams in both the screen. So in this also, so at the 14 radian per second, the building will respond like this. And if I will increase the frequency of the earthquake, then it go like this. Okay, then it go like this is at the mode 3. You can see what is the mode number 3. Now go for the next mode, that is our mode 4. In the same way also, this is the mode 4. Okay, now I increase frequency more than more, it's our mode 5. You can see this is the most, means it will become at very high frequency. This type of response we can see at the higher frequency. Okay? Now I will increase the modes natural frequency again. So this type also, because the frequency for this type of response needed very high. Okay, now I go further. So this type of modes, why it will come, can anyone give me about idea, like why it will respond like this? Due to which loading? So this is due to what? Dead load. Okay, I increase the mode. This is all due to load, dead load once again, because dead load can make this type of modes. Now go again. This type only for dead load. So at this type of frequency you can get this type of response of our building. So I stop this here. So now you can relate the you can relate the building response with your natural frequency of earthquake, and how your building will respond under this frequency and under the, so you can plot the frequency plot also. So this type of higher educations I will give little bit to you in next series, lecture series, because the SAP results are also important for the design of building. Okay, by this way you can design any column and beams and slabs, that is more easier to understand. Okay, so thank to all, meet you in next lecture.